Here is a close-up of a star formation region, and this is a really nice H2 region, a reflection nebula, if you will. So the first deep sky object that's associated with the star formation region is N159, the Papillon Nebula, which is in the Large Magellanic Cloud. This is actually quite a rare observation. This is a very young pair of stars, two massive stars, about 10 solar masses each, very newly formed. It's pretty rare to catch a massive star this young in its development. That's young astronomically speaking. They're about 10 million to 100 million years old only. And these stars are very massive, but they're still embedded within quite a disk of gas and dust, which is still infalling, trying to drop onto the surface of these two stars, still increasing their mass. But now they're emitting so much radiation that the radiation from that star is pushing that infalling material away into this lobate structure, this sort of butterfly-shaped structure that you see. The other star formation region that is a deep sky object this year is the Trifid Nebula, M20. This is a beautiful star formation region, and it has a little bit of everything. We have massive stars forming here, emitting enough radiation that here we have the red emission nebula where the gas and dust has been heated. It's now emitting its own radiation. We have this large blue area where the ultraviolet radiation from the developing star is being reflected from those clouds and directed towards Earth. And then we have this dark clouds, the dark nebula that are left over from the molecular cloud, still pieces of it overlapping the emission and radiation nebulae, which are both H2 regions. If you right here in this particular area, a more close-up, and here is, we're starting to see the outline of one of my favorite images of all time, this close-up right here. Now you can see more of the structure of the dark nebula. And right in here, if you close up even more, is this really shows the photoevaporation that is destroying the gas and dust coming from this protostar that's now emitting a lot of ultraviolet radiation. So it's sculpting these beautiful pillars. Right here, there is a stellar jet that's coming from some protostar still embedded within this cloud. And right here, there is a small star trying to develop in this little clump of gas and dust. But the emission, the radiation from this more massive star behind this larger pillar is evaporating away that dust pretty rapidly. So this is an example of how inefficient star formation is. It's only about 10% efficient. So only about 10% of all protostars actually make it to the main sequence, become real stars. You will come across the term young stellar objects. Young stellar objects refer to both protostars and pre-main sequence stars, and there is a difference between the two. Protostars are stars. All of these are examples of protostars. They're still deeply embedded, or at least partially embedded, within the molecular cloud. So there's a huge amount of gas and dust surrounding them. There's a lot of material infalling onto the surface of these protostars as they're accreting more and more mass. They are very active, though, because there's a lot of energy produced by the infall of material. And it produces a lot of jets and outflows, and so they are very, very active. But protostars, not all protostars will end up becoming main sequence stars. The ones that end up being, some of them will become pre-main sequence stars, and some of them will never reach the main sequence. The pre-main sequence stars, we'll get to in just a moment, the difference between the protostar and the different pre-main sequence stars. These protostars are surrounded by a protoplanetary disk. And so there's a huge disk of gas and dust still surrounding these protostars. They are still accreting mass, becoming larger and larger, lots of infalling material. And this Chandra animation is a good example of what's happening with these protostars. As I say, they are very active from infalling materials. They emit prodigious amounts of high energy radiation. Those waves of radiation, including X-rays, move out through, send shock waves through the protoplanetary disk that sweeps any of the debris away from the star into the furthermost reaches of that disk. Eventually, there will not be any material left closely to the protostar, and the infall of material stops, and the mass accretion stops, and then they remain that mass throughout the rest of their stellar lives. Now, this is a different kind of circumstellar disk, the debris disk, and it can be thought of as sort of a stage in planet formation that is preceded by the protoplanetary disk. Once that protoplanetary disk is sort of cleaned out near the star, and infalling of material and accretion of material onto the protostar stops, then you have this debris disk. Within the debris disk, you can have accretion now of materials, the gas and dust, that will now clump together and start forming planetesimals, which will then start to form planets. So that's a difference between a protoplanetary disk and a debris disk. Now, there are three specific types of pre-main sequence stars, and the difference between these and brown dwarfs, which are also pre-main sequence stars, is that these objects will actually end up on the main sequence and become real stars. Three different kinds we have here. The Herbig A, E, B, E stars are the most massive ones. These are B and A stars with a mass usually between 2 to 8 and 10 solar masses. And then we have the TTauri stars. We've had TTauri stars almost every single stellar evolution event. Every single year we usually deal with TTauri stars. It is a pre-main sequence stage of stars that are less than 2 solar masses, and they are generally F, G, K, and M stellar classification stars. The Fuori stars, the Fuors, are a special case of a TTauri star, usually right about 2 solar masses, where there is a lot of infalling of material, mass transfer from the disk to the surface of the star. The Herbig AEBE stars, the BA mass stars, not too many of those have been discovered, and you probably will never catch a pre-main sequence stage of a more massive star, because those stars are so massive, their fusion processes take place so rapidly that they are basically on the main sequence before they even become visible. So there aren't too many of these objects that have been detected either. One of the deep sky objects, TW Haya, is a TTauri star. It is still accreting material from a protoplanetary disk. Within that disk, at one time they thought they had detected a planet, but further study determined that it was not a planet. But there's still the possibility of planets within the forming within the protoplanetary disk of this deep sky object, because it has a ring of frozen water vapor. So there is a huge amount of water and other materials that make this a really strong possibility for exoplanet development. Fuori, which is the prototype of all Orionis type of stars. As I said, these are a special case of a TTauri star where you have massive transfer taking place from the disk to the surface of the star. And these stars are rotating so rapidly that they're rotating much more rapidly than the incredible magnetic field lines that they're producing. And as these stars rotate, they rotate faster than the magnetic field lines, and we see this in the sun too. So it can rotate so fast that the magnetic field lines become disconnected, and then they reconnect again. And when they do that, they emit enormous amounts of radiation. Remember, this is all coming from the rotational speed and from the severing and reconnection of the magnetic field lines, not fusion.